Now let's have the recording started. All right. Welcome all to the FutureChips launch event of our call, which is now open. You will hear more about the call, but now first we would like to tell a little bit about Tampere and Tampere University. And here you see the program. So after presentation of Tampere University, you will hear more about the chips from Tampere, the actual program, FutureChips, and then also a few then supervisors and research group leaders will present their research group. Pauli, if you continue from here.
Okay, thanks, and good morning or whatever time of the day you are having. It's good to have you here, and it's a great pleasure to officially open this call. And I do it very quickly, let's say the background. So starting what kind of city Tampere is. And well, I would say that it's the best city to live. So I have been there already some 40 years almost, and lived in other places, but love to live in Tampere. So it's a pretty small place, as you see the numbers there. So it's not a huge one, but it's large enough so we have everything that we need, and it's very clean, very safe, and good education, and in many ways. So it's really great, and we are very proud of course, our university, that I will share some words, but and we consider that it's very important in the field of chips and semiconductors, and we have really good reasons to claim so. So quickly about Tampere University. So it's a second largest university in Finland. So it's truly multidisciplinary. So we have health there, we have SSH, we have technology, and actually we have also 3 locations for the campuses, but all these places that are now opened, they will locate at Tampere. And there you see the numbers, so that around 10% of our students are international ones, and even more in the employees, and especially in the fields of technology. So over 50% of the employees are international ones. Altogether, we are operating close to 400 million budget, and out of that, some 120 million is coming from competitive funding that we apply all the time. Next one, please. We have brand new international strategy. I don't go through all the details, but just letting you know that the being truly international is very important for us. And under the strategy, we have there the 4 themes that you see there, so that we try to be really a thriving university community, accept the diversity of the people, and embrace it, and try to provide every nationality, every member of the community possibilities to influence and participate. And then our goal is that we are really an internationally esteemed research university, and we are pretty good at that. At the same time, we truly try to educate our world-changing experts, and all in our degree programs, internationality is important, and I can really say that basically all our master level courses are taught in English. We have some exceptions, like in healthcare, where also the Finnish language is important, but especially in technology, so all the courses, master level courses, are in English. And as we have the strategy, so we have the strategic approach to the internationalization, and we try to really influence globally. So don't do just research for research sake, but the goal is to be really an influencer. Next one, please. And what we really try to do is to really utilize the multidisciplinary nature. So like I said in the beginning, we have technology, health, and society, SSH. We try to combine them whenever it's possible. This is really an asset if we are able to make that very well. And of course, the research should be conducted responsibly, and we really promote open science. Basically, all our publications are opened. And state-of-the-art research infrastructures are truly needed, and especially in this call, we emphasize a lot them. So please consider carefully when you apply this research infrastructures that you study what we have and then propose accordingly. Next one, please. We are pretty good at obtaining the research funding from EU. So this is from the Horizon Europe time period. So currently in the Pillar 2, which are the joint projects where industry and universities are collaborating, we are number 14 in terms of the funding achieved from the calls. So this is pretty good result, or quite impressive actually. And it indicates how closely we are working with the industry. And in CHIPS JU, we are really active, or CHIPS Act, whatever you call it. So we participate. We participate in the pilot line in this advanced wide bandgap semiconductors. There we are in the packaging end. So we have a system in package fab under construction. We are a member of the design platform, which is under construction. And then you will hear more about the CHIPS Competence Center. We also participate in a design enablement team, which enables the newcomers to the field to really start to learn how to design chips and how to even fabricate them. So we are one member of this design team. And then we also participate in this CDP funding part, which provides funding support for the newcomers. So we are everywhere there in the CHIPS Act, and we are proud of that. Next one, please. And here you see some of the reasons why we have this program, why we were accepted, and what are then the key elements where you can apply, why we have chosen these 4 topics that you will soon hear more from Jörg. So we are coordinating the flagship of photonics research and innovation in Finland. So we are very strong in photonics. So we have a systems on chip hub research center for that, and actually so this design of the SOCs is very important for Finland, for Tampere. For example, Nokia's most advanced chips are designed in Tampere. And then, like I said, we have this system and package fabrication pilot line, and also from this list you see the key names. But thanks again, and I really hope that we will receive a very good number of great applications, and it's a fair competition. Best ones wins.
Thank you, Pauli. And we progress to Petri Räsänen to hear more about chips from Tampere.
Good morning on my behalf as well. So this is Petri Räsänen from Business Tampere speaking. Business Tampere is a very close partner to Tampere University, and we are the economic development agency for the whole Tampere city region, covering almost 400,000 people area in and around Tampere. Next one. So Chips from Tampere program is one of the kind of strategic development programs of city of Tampere. And so far we have been in operation for 2.5 years, almost 3 years. And during our first phase of operation, in the phase number 1, our key objective was to kind of make sure that Tampere and Finland will be closely integrated with the European Chips Act. Next one, please. As Pauli was already mentioning, the results of this first phase of the program, they have been very good and maybe impressive even. So the previous one, please. So the Finnish Competence Center was established to Finland and headquartered in Tampere. Tampere University is a member of this European Design Platform development and partner in wide bandgap packaging and system in package development, and also the kind of national policy integration was secured with the close collaboration with Business Finland. And what is also a very important part of our program, that we have been opening new collaborations across EU towards US, to Taiwan, Japan, and Singapore. And maybe the latest milestone was the kind of MOU that we agreed with the Dresden region in Germany, where the leading semiconductor manufacturing hub for Europe. The next one, please. And now, when we are moving to this phase number 1 to phase 2, we will have some revised and even more updated and targeted lines of operation. But the overall targets of the program will remain. So we are targeting at establishing new design centers and startups to Tampere. We are targeting at making the SIP fab operations and the pilot line operations a sustainable part of our ecosystem. And finally, we are targeting at attracting industrial fabrication investments to Tampere based on our strengths in various areas of semiconductors. Next one, please. And the work packages in our program, they include these 4 areas. First of all, we are targeting at the EU Chips Act version 2 and make sure that Finland will be successful there as well. We are attracting and preparing the soil for industrial investments. We are kind of boosting collaboration in the area of talent development between the companies, the educational institutions in the region and in Finland and in Europe. And fourthly, we are working to make the ecosystem collaboration and cooperation in the region as fruitful as possible for companies and the talent that we are developing in the region. The next one, please. So we are moving forward to the Chips Competence Center, but overall, maybe from the Tampere Chips program point of view, we are in the middle of very long-term development, and the region is fully committed to the long-term development of the ecosystem in the region. Thank you very much for joining.
Thank you, Petri and Josre. So Sama. Now, possible?
Yes,
please,
if you may, I will share a couple of my own slides.
Yes.
Okay. All right, so Finnish Chips Competence Center. We are EU project, funded half by Chips joint undertaking and other half comes from Business Finland, so the national funding. So the Chips Competence Center, it's actually under the EU Chips Act Pillar 1 Chips for Europe initiative. So Europe is actually establishing these competence centers in all of the European countries. We are almost 30 competence centers at the moment, and the main task for us is to operate in between the semiconductor startups and SMEs, and then collaborate with EuroCDP and the pilot lines, which are now under construction in Europe. So we are the kind of gateway to those instances, but not limited, of course. We aim to boost the local semiconductor industry in Finland, and as our friends in other European countries do the same in their respective countries. Here, just showing the map. So we are the Finnish Chips Competence Center, and as you can see, we are forming a quite nice network of competence centers. So this gives us a nice view of course, the companies in outside of Finland, but also the research infra and all the opportunities which then our companies, especially startups and SMEs, can utilize. Just quickly showing what is the competence center all about. As I was saying, on the top left, we are under this Chips for Europe initiative. Okay. But on the other hand, our competence center project, it's also following the Chips from the North, National Semiconductor Strategy for Finland. So it's a 10-year strategy defining the growth opportunities, as you can see here. Chip design, photonics, MEMS, quantum computing, so on. And we have also outcomes, which we try to then actually follow, and we are in the operative mode that we try to then be in line with this strategy and help boosting the local semiconductor strategy. We do collaborate a lot with the universities, as you can see with Tampere University, but also all the other universities, especially Aalto University and Oulu University, who are among Tampere the three biggest universities in terms of semiconductors. Also, VTT is very close to our operations. As I was saying, our aim or our motivation is to boost the local semiconductor industry. We don't limit to that sector. Since Finland is a rather small country, we are also collaborating with other sectors such as space and defense, intelligent work machines, health sector. So trying to find companies, people, interest among those if they could utilize the Finnish chip design or manufacturing expertise, or at least the European, all aiming that we should be more sovereign against the Asian and US technologies. And just the last slide showing, so CHIPS Competence Center in Finland, we are a consortium. Chip Fusion, I'm working for Chip Fusion. We are coordinating this project from Tampere region. Our members are Quantinova, very close to VTT and this Espoo chips ecosystem. Then we have Photonics Finland, on the eastern side of the Finland, and then we have Business Oulu, who is taking the northern part of the Finland and the chip ecosystem there. So I will stop here, and thank you.
Thank you, Bas. Hope you can see the slides. And now we will transition from Tampere and Tampere University to the actual FutureChips next generation semiconductor technologies postdoctoral program, which is co-funded by the EU under the Horizon Europe Marie Sklodowska Career Action. You find here the contact address and also the link to our FutureChips webpage. Within the program, which will run for 5 years, we have 4 research areas, and we offer 20 postdoctoral fellowships in 2 calls. The first call is now open and offers 12 positions, and then the second call will open thereafter with 8 positions. All fellowships are then having a duration of 36 months, and you can apply then from now until the end of August. So 31st of August is then close of the current call. The 12 postdoctoral fellowships will be then implemented at 2 faculties, the Faculty of Engineering and Natural Sciences and the Faculty of Information Technology and Communication Sciences. The call is already open, as I said, closing at the end of August, and you as an applicant propose your preferred specific research project, which has to fit to one of the 4 research areas, so advanced compound materials and heterostructures, novel architectures, chip design, and then advanced packaging. Technically, you select a research area in the submission system. You select also then the primary academic supervisor active in that research area. And for you, as an information, all the 12 fellowships, they have a monthly gross salary before taxation of 4,500 euros, which roughly then means after taxation 3,100 euros. Here you see our 23 academic supervisors, as they have been linked to the 4 different research areas. And since we have a time restriction for one of our research group leaders, so I will invite Professor Mircea Göner to then now just present briefly his research group. Thank you.
Thank you. Jörg, can you hear me?
Yes.
Can you also see me?
Yes.
Okay, great. Thank you. It's a little bit difficult. We are having the holidays, but I am very glad to have a chance to present a little bit of our detailed activities. You can find the area or more details about my activities under the Optoelectronics Research Center group, which is part of the photonics group's links, and we are part of the Faculty of Engineering and Natural Sciences. Please, let's go to the next slide. Well, I think that in the area of chips, what we could say that Tampere University provides probably the most comprehensive type of materials, heterostructure devices when it comes to the 3-5 compound semiconductors, meaning that, well, we have a long tradition in molecular beam epitaxy, and we are using molecular beam epitaxy for developing gallium arsenide, indium phosphide, and gallium antimonide heterostructure. We have an attempt, a task force to move also towards gallium nitride, which may come in the life of this project, but not yet. And well, this diversity of materials allows us to tackle a lot of problems let's say, or provide solution for photonics application at the device level. We do, let's say, advanced fabrication of semiconductor lasers, detectors, solar cells, photonic integrated circuits in a form of design, but then we are using external fabs. And maybe the most important part of activity in the recent years has been the transition towards advanced packaging and submicron assembly technology for photonic integrated circuit, but not only. Yes, you will see a lot of let's say tools. There are even more tools listed under Finlight website. I will not go more in details, but I will just say that our infrastructure in the area of compound semiconductors and fabrication of optoelectronics, it is state of the art. Please, let's go to them. Yeah, so we are running a comprehensive set of projects. We have project portfolio in the range of 1 to 1.5 million euros, largely in 4 areas nowadays. One, it's laser sources, customized semiconductor laser diodes, and other type of optoelectronics devices like detectors. Then we have the photonic integrated circuits, which is run as part of 3U projects. Currently, you can see details about these projects under Raven website, and then under PhotonMed. Raven, it tackles development of photonic integrated circuits for gaze sensing, and PhotonMed for biomarkers. Then on the more basic science or basic technology side, we have the development of quantum light sources. I will have a separate slide on that. And then cryogenic optoelectronics or cryogenic photonics, development of optical links for cryogenic computers. These areas of project is, let's say, it's run a group with a good size, with a comprehensive, again, skills from material science to fabrication and application development, together with 2 co-PIs. One is Professor Jukka Viheriälä, which is in ITC, and he will also cover more on the packaging side. And then Teemu Hakarainen, which is covering the quantum light sources. Please, let's go to the next slide. Yeah, so I'll give three highlights of the main research areas now, and the applicants can get an idea what we are aiming and where do we position against state of the art. So in the area of quantum light sources, we have quantum dot-based system based on gallium antimonide heterostructure, which allows generation of single photons and entangled photons at telecom wavelengths. And this activity is now covered by a ERANET program, European program, and also by a strategic program covered by Business Finland, where we aim to develop our own quantum key distribution system for on-demand sources. What we are aiming in this area, or what we are looking to expand our expertise, is fabrication of advanced devices where we are working on extracting improving the extraction efficiency of the, let's say, quantum light, single photon or entangled photons. Please go, let's go to the next one. In the area of hybrid on photonic integration circuits, we have been working a lot on the hybrid lasers, meaning lasers, semiconductor laser with advanced functionality enabled by photonic integrated circuits. There are quite a few papers published, and these are just a sort of snapshot of current projects. We are developing lasers at 2 to 3 micrometers, targeting broad tunability. It's the left figure. Or then multi-wavelength lasers for gas sensing, or narrow linewidth lasers for also gas sensing, but also other application. And this activity, it's a very good level to tackle application. So we are also offering a possibility to work on application. And let's go to the next slide. The next slide is about cryogenic optical links. So we have been, what we try to solve, it's provide a light-based solution for scaling of superconducting quantum computers, where we need to send microwave fields to superconducting computer or read out quantum states from the cryogenic environment. So we have been working in the recent years, and you should see recent publication concerning VCSELs, or vertical cavity surface emitting laser, at very low thresholds, and then operating at 4 Kelvin, and then detectors. Again, it's an area covered also together with Professor Jukka Vihejala. And I think that was my last slide, Jörg. Yes. And just one comment from me, I will not be able to stay, or I'll try to take over the phone the last part of the meeting. If there are questions, I will be on Friday in Tampere, and people can contact me on email if they need more. And please feel free to share these slides. Thank you.
Thank you, Mircea. So, as I showed you, we have 23 academic supervisors. Each supervisor is presented on the FutureChips homepage with a short then statement on the background, the research group, and the research infrastructure. There are links then also to more information, for instance, on the publications. Those are all under Tony Chris Research Portal. And then also you find a link to the ORCID of the individual research group leader. Now back to the application and the application requirements. Since, as I said, FutureChips is co-funded by Horizon Europe under the Marie Curie sub-program. So the program has also to adhere to the Marie Curie Scholarship Curie Actions terms and conditions. And one of these is that the applicant cannot have resided or carried out his or her main activity in Finland for more than 12 months in the past 36 months immediately preceding the application deadline. As I said, closing of the call is on the 31st August 2026. And in addition to the mobility criteria, of course, since it's a postdoctoral fellowship, you have to have a doctoral degree in a relevant field. In case you haven't yet received your certificate, there is also the possibility to still apply. And you see here some information on that, more information on the guide for applicants. And then since you propose your own individual research, you have to have the ability to pursue independent scholarly activity, and then the English language skills are, of course, also relevant in this program. Submission documents. Technically, you only submit 2 PDFs. One is a doctoral degree certificate, and then the application. The application contains a research plan abstract, the research plan itself, the CV, list of publications, an ethics self-assessment, and a one-page motivation layer. You find more information on the position on the internet. There's also on our FutureChips webpage, the guide for applicants, and please use our application template, which is as well available on the FutureChips webpage. It's a Word document, and you can then use it to submit your proposals there. On the evaluation and selection process, all then applicants will be evaluated based on the same criteria. Those are the academic merits, the quality and scientific excellence of the proposed research, the feasibility, impact, and implementation of the research project foreseen, and then the scientific relevance and significance of the proposed research topic, and communication and dissemination skills. As then Pauli Kursmanen already indicated, please check that your research infrastructure required to implement the proposed research also match what is available at Tampere University. You find information about the research infrastructure on the webpage of FutureChips as well of the individual research groups. And then also then the research plan proposed should then be implementable within the chosen research group, and then also should have a link to one of the 4 research areas. Evaluation process call closes in August. Then each eligible application is evaluated by 3 independent experts external to Tampere University. The applications are ranked by scoring. The highest ranked will be invited to an online interview. The online interviews, less than 30 minutes, will take place then towards mid-end of November this year. An ethics screening will be carried out, and you have also the possibility, if there are procedural errors in the process or factual inaccuracy, then to submit a redress request. The recruitment decisions are foreseen to be taken at the end of this year, and you see also information to candidates then in January next year, and we will publish the results of the selection process, and the fellowship starts then in July 2027. So we have different then information for you then compiled on working in Tampere. And since there is a period between the information to successful applicants that have secured a fellowship in January next year, and an official start of the fellowship in July 2027. So we will have a hosting agreement to be signed in early 2027. All fellows have to relocate to Tampere and then have to be in Tampere when the fellowship starts at the latest in July 2027. Just to show you that we have on the slide set then also a couple of information on the relocation services offered to you by Tampere University as well as the city of Tampere. And there are more information on Finland, the city of Tampere, and then working at Tampere University. And now we proceed then to a couple of presentations of research groups welcoming fellows to work then at their research group. And we will then continue now with Gary Ganti.
Yes, can you see me and hear me?
Yes.
Okay, great. Thank you so much. So good morning, everyone, and I'm very glad to be present today to introduce what we do in our group and potential ideas for collaboration within the framework of the FutureChips program. So I'm Guéry Gentil, professor of photonics at Tampere University, and I'm also the director of the photonic flagship at the university. And I'm not really coming from the classical semiconductor fabrication side, but rather our group is trying to address the question that once we have advanced materials and devices, how do we make them to perform something useful and programmable in terms of optical functionalities. So my own research has been mostly at the interface of ultrafast optics, nonlinear dynamics, complex light fields, and more recently, we have added some elements of machine learning control. So Mircea has just shown you before in his own group the material and device fabrication side of the research area here. And what we bring is a slightly different angle. That is, how do we use nonlinear light matter interaction to generate, convert, structure light? So our research group background so far has been mainly in ultrafast and nonlinear photonics. We have often used optical fibers as a very flexible test bed. And now our new research direction is moving towards chip scale platforms so that we can turn nonlinear complexity into useful chip scale functionalities. So if you're interested in nonlinear photonics and you want to connect your work to future technologies, this is where my group fits, essentially. Next, please. So the basic idea is rather simple. Nonlinear optical systems are complex, but that complexity can in fact be very useful. So we do not see nonlinear propagation as something that distorts signals or make them unstable, but rather we see nonlinearity as a resource, which we can engineer to create new wavelengths, new pulse shapes, new sensing modalities, or new computing concept, for examples. And what makes this, at least from my perspective, rather exciting is that light can be structured in many dimensions at once. We can structure it in space, time, and frequency. And once you combine that with waveguides, multimode systems, and nonlinear effects, you can get very rich physics. But of course, the challenge, and also, actually, I see that as an opportunity, is how to control those. And the FutureChips program is a very nice framework for this because we can turn very rich physics into useful, compact, programmable photonics functions. Next, please. So this next slide is really more about what a fellow would get by working with us. So we are not a primarily fabrication group, and I do not want to say otherwise. But the value we bring is really the bridge between material or device concept and experimentally validated optical functions. So what that means in practice: ultrafast testing, spectral and temporal diagnostic, complex field measurements, numerical modeling, programmable excitations, and closed-loop optimization using machine learning. So this can be very important for nonlinear devices because the base operating point is usually not obvious. It depends on many characteristics of the chips: the dispersion, coupling losses, phase matching, power handling, fabrication imperfections, and so forth. So the role here is really to help turn a chip from something that has been fabricated to something that actually works and is optimized and physically understood. And last slide, please. So these are not fixed project title that our group is looking for. Is rather more starting points for applicants to build their project and some suggestions. But of course, these are non-exhaustive list. So for example, we would be very interested in project on thin film lithium tantalate chips, where we started some research on for efficient nonlinear optical functions, frequency conversion, supercontinuum generation, parametric gain, pulse shaping, or modulation. Another direction could be molecular sensing. Can we use chip-compatible nonlinear sources to reach useful wavelength regimes, for example, in the mid-IR, for gas biomarkers or environmental sensing? We are also very interested in adaptive and intelligent photonics, where one uses machine learning to control nonlinear devices or using the nonlinear transformation itself as a physical computing layer. So the profile we are looking for is someone who likes to work at the boundaries from materials to devices and from devices to ultrafast nonlinear experiments. So if you want to make nonlinear photonic chips to do something useful, reconfigurable, and maybe a little unexpected, I think this is our group would be a great fit. So thank you very much for your attention.
Thank you, Guy. And then we move on, and Sayana.
Hi, can you see me and hear me?
Yes, thank you.
Great. Thank you very much. Good morning from my side as well. And thank you for joining this call and your interest in applying for this FutureChip program. So I am representing this CMOS and Beyond Devices and Systems Research Group from the Faculty of Information Technology and Communication Sciences. So this is our team's current composition, 2 postdoctoral fellows, 6 PhD students, and 2 master students. And we also have the fabrication lead, Dr. Soizara Sagasapa, who is currently working as a fabrication engineer in SIPFAB. So while the name CMOS and Beyond, we don't do exactly only beyond CMOS computing, but because CMOS has been developed for more than 75 years and it's going to be there. So our target is to develop let's say systems which use the maturity and excellent properties of CMOS and go beyond in computing. And here we are showing, let's say, some of the key targets of our research and development. For instance, neuromorphic, edge AI and quantum hardware mainly for cryogenic computing, cryogenic memories, and in-memory computing circuits. And our group's one of the major focus is performance reliability, both device and systems level. So we use AI-driven material and process design for these tasks. Then we keep ourselves, let's say, confined within the back end of line compatible materials and processes so that everything can be integrated on top of CMOS circuits. Also for European Chips Joint Undertaking project, we develop non-volatile memories and in-memory computing circuits operating down to deep cryogenic temperatures, which can be used for quantum hardware, but also for space applications. And another key architectural side of us is 3D integrated sensor memory and logic for edge AI hardware. Currently, we are focused on 2 different applications. One is healthcare, where we are doing arrhythmia detection using spiking neural networks. And then other is autonomous vehicles, where multi-sensor fusion and decision-making takes place at the edge. Next slide, please. Yes, so we are on the fabrication side. We design our own chip. We fabricate it. We have facilities both in Tampere University, and also we use the national research infrastructure in Espoo, which is Micronova facilities. So we fabricate our own chips, and this is one of the picture of the devices developed within the team. Next slide, please. And what kind of devices we mostly work on is ferroelectric thin film capacitors, then back-end of line compatible transistors, so ferroelectric field effect transistors, mostly working on oxide like indium gallium zinc oxide or 2D semiconductor like MOS2W thin film transistor based circuits and systems. So basically, the MOS2 or IGZO, they both have also sensing properties. So the idea is not to do only memory and data processing, but at the same time sensing at the edge. So basically in-sensor computing is one key target. So development targets within the group, within multiple ongoing projects, is to develop this low power nanoscale 3D integration of resistive and capacitive in-memory computing, And in the future, like in FutureChips project, what we would like to develop is also self-powered, so self-sustainable systems, also keeping hardware security in mind, and also including novel functionalities, both device and systems level. You can get more information from our webpage about all the ongoing projects and current development goals. But I can also quickly say that this is one of the future targets, that we will have all sensing, memory, and logic layers incorporated directly with the vertical integration structures. And for the bottom two layers, memory and logic, we have already started working on this in the CHIPS Joint Undertaking Program. So with different companies and other research partners like Fraunhofer and other European partners, we started already getting 3D vertical integration of memory and logic circuits. And finally, the idea would be to also add the sensing layer and, as I said, self-powered systems. The next slide, please. And this is some recent results from the team and the articles, if you want to go to the details of the results. But very quickly, we have the world record of getting low voltage operating ferroelectric memory, showing operation down to 4 Kelvin, and without any fatigue or any device failure. That is one key achievement during the CHIPS JU project. Then together with National Science Foundation US, we have this near sensor computing architecture developed, where sensing and computing happens all at the edge without need for data communication to the cloud. Then we have development on the physics-based compact model for the ferroelectric memories. Then with big companies like Applied Materials, we have developed the capacitive in-memory computing and hyperdimensional computing systems, which will appear soon in Nature Microsystems and Nanoengineering. And another important ongoing activity is on the sensor fusion and decision making at the edge. In the autonomous vehicle, where multiple sensors like camera, radar, LiDAR, and all those act together, and their reliability and let's say decision making at the edge is what determines the performance and safety critical applications. So we are mostly working on these fields, but also some other incoming activities, let's say in FutureChips or in other projects, will also, let's say, strengthen activities in these areas. So I'm happy to discuss more about any new ideas and develop any plan based on your research expertise and your research interest. Thank you very much.
Thank you for presenting. And we move on to Professor Matt Ventusalo.
Hi, thank you. Can you hear me?
Yes.
Yes.
And I can see you.
Okay, perfect. So first of all, really a pleasure being here today, presenting shortly on our work. I'm really excited about the whole FutureChip project. So first of all, something about myself. My research focus is mainly on electronic materials, fabrication, and also thinking about the scalability, how we can do that, and form factors of those. So if we talk about the focus, it is really on printed and additive technologies, thin film devices, energy storage unit, and how to make these integration. And Jörg, we can go on the next slide. So here more detailed, if you are interested on the left-hand side, you can see the activities that I'm doing. So connecting, making interconnections, creating flexible, stretchable devices, some supercapacitor and harvesting part, and then thin film devices. Highlighting here with green the most important for the future chips related activities. So if you think about interconnections, you can replace by additive technologies and novel materials, replacing the wire bonds, creating a system in package. We have demonstrated some. I will show you a few examples. We have done different stretchable electronics interconnections to really create a new form factor for integration. And then at the last, I just want to highlight we have built thin film devices, even tunnel diodes. How we do this is using a combination of printed electronics and other technologies. One of the things that I want to highlight here is laser assisted ALD, which is something that we have developed recently by ourselves. We are soon to be publishing, unfortunately, nothing big yet out yet, but that's definitely something to consider. I'm more than happy to discuss about it. But then we can go on the next one. So here you can see a couple of examples of the heterogeneous integration. So what does I mean with it? It's like we are taking a part of the conventional electronics, like MEMS device you see here on the right hand side. That's a cross section of a accelerometer, and there are a few elements like functional materials. You can print gather materials. You can do the connections to device to handle layers, creating of the redistribution layers, and we have also demonstrated the through silicon vias to do the metallization. So you can take a look on that. Then on the right hand side on top, we can create different kind of micropillars and microstructures for flip chip bonding, for example, and bottom right corner. There you can see an example of how you can utilize an inkjet printing or additive technologies in general to create system and package and connect passive components and active components together, build the complete system. And just as an example, we demonstrated already 10 years ago, or maybe even more, how to integrate complete half GSM baseband with this technology. And then we can go on the other topic. So the other topic that I'm bringing here on the table is the thin film fabrication. In this one, we have been previously demonstrated flexible circuits. You can see that one on the left-hand side. That was the world's first all printed, fully printed thin film charge amplifier for on-skin biosignal monitoring. We have different sensing elements that we can put over there. So these devices are based on either organic or inorganic semiconductor devices. Another aspect over here, how we are doing is a combination, as I said, printed and different atomic layer deposition, for example. You can take a look on the plasma enhanced ALD and how we build up the half film oxide for the gate dielectric. And the similar approaches are now we are going to do with a laser assisted ALD, where we can already we have shown that we can grow even in 50 Celsius degree with the assistance of the laser, really high quality aluminum oxide films. But then let's go on the next one. So shortly, just saying a few words, what I'm offering here, if you want to collaborate, there are world-class infrastructure in general in Tampere University, but for example, the lab that I'm responsible, the Laboratory for Future Electronics, that's also a part of national coordinated printed intelligent infrastructure, which is a combination of 4 institutes in Finland. So you can take a look on that one. We have a nice funding until from 2019 to 28, so it's a 10 years program of funding for it. And you can see all the details of the equipment, and you can ask more details from me or our staff scientist, Jari Keskinen, if you are interested in something on there. And then from the research-wise, what I'm more than happy to discuss and collaborate and see if there are any opportunities, hearing your ideas, what can we do in the terms of additive technologies and heterogeneous integration, how we can combine different materials, creating either 3D structures, 3D architectures, or flexible stretchable connections. Those are important for many wearable electronic applications, soft robotics, and so on. So there is a lot of elements over there. The research programs can be related to the structure itself or materials or how the combination of these ones. And then on the thin film devices, so this is more on the category 1, you have mentioned in early, how we could build up using these, let's say, interesting new ALD processes and how we could get with the nanolaminates new features for the devices to create flexible electronic devices. That's short. Thank you.
Thank you, Matti. And next is Juha Toivonen. It's then the 5th presentation. Would have been lovely to present all the 23 research groups here. Time doesn't permit this, so hope that Juha can connect.
Okay. Hello, everybody. Also on my side, good morning. I try to be short with this to get in the questions part. So my group is in a I'm Professor Juha Toivonen. My group is in a applied optics area. So we are doing optical spectroscopy applications, and there is some list in this slide about what kind of applications. So there is gas sensing on different kind of gas sensing applications, also elemental analysis, LiDAR analysis, or some analysis of drinking water quality or radioactive sources detection and so on. So quite variety of applications, and also collaboration with the company. So there is some patents granted and pending ones which are typically together with the company collaborators. So that's a generic area where my group is working. If we go next slide, and then the facilities where the project can be run, we have heard already many directions. This is more like an overview of the photonics facilities in Tampere University. So we have a clean rooms around 1,000 square meters currently, and another similar 1,000 square meters coming up, which is exactly on the packaging concentrated or focused EU pilot line clean room, which will be then available at the end of 27, which is kind of good for these projects too. There is a lot of optical testing facilities. We have like in total almost 20 optical laboratories with the optical tables. So there's a lot of space to build a testing sites then for the structures that have been built. Okay, next one. So I wanted to raise here from the facilities point the packaging and assembly systems, because that's when we are doing sensing on the chips. It's typically contains putting together light source, waveguide, sensing area, detectors, maybe some electronics to drive them. So then that's why the assembly stations are important from the sensing applications point of view. And I wanted to raise here the facilities that we have on that direction. So in principle, we can package together components quite well already, and then this new clean room with the extra capacity on that direction will of course then even give more possibilities on that direction. Next one. So sensing often happens in a mid-infrared wavelengths, but our group is working actually from UV wavelengths, 180 something, to long wavelengths in an infrared, like 10 micron, 11 micron. So all that wavelength range, and then you need to think of a different structure to operate in a different wavelength range. So that might be part of something that could be in a project to look for new wavelength areas. But in principle, we look technologies like direct absorption, but also Raman, stimulated Raman, photoacoustic fluorescence. So the actual sensing method can be from a quite variety of interactions. Next one. This is the last one from me, kind of the potential project areas that could fit to my group area are structures for sensing, like waveguides or sensing methods that can be integrated in the smaller chip scale, or then actual packaging together, demonstrating the new functionality of sensing in the small chip scale, and then of course validate that. For example, these examples here are for gas sensing, but it could be also liquid sensing, whatever is in your mind there on the sensing applications. That's all.
Thank you,
from
Juha.
me.